So for today, you may be relieved to know there is no quiz. Just as a reminder, though, I did put in the announcement I did send out. There is a timed lab this Thursday for you guys, right? Since your lab period is on Thursday. The timed lab is 3% of your grade. The questions are much like the questions that you had for homework 2. Okay? So homework number 2, so they're going to be the same kind of questions there. And you guys will have about an hour and a half to work on it. You guys can have the whole, that's about the time. We're still going to collect data on how much time we need, but you guys are going to have an hour and a half. I don't think it should take that long, but when you're coding on a computer, you can sometimes get into errors. You can sometimes get minor weird things that you didn't need. You can create and put in bugs that you never meant to put in, and that can just drive you crazy. So that's what I'm going to avoid. This week, we are actually avoiding doing much programming at all, other than finishing up what you already are doing. So instead, I'm going to open up so I've done 2 things, one of which I've never done before. So let me start with the thing I've never done before, okay, because it's easier to segue off the other stuff. And I've released a 10-point extra credit assignment, which is due anytime through the duration of this class. Okay. Now this one is on regular expressions, and you can do this in any language. Any language. You can do it in Python, you can do it in C, you can do it in Bash, you can do it in Java. Because regular expressions, once you learn them, they are language agnostic. Almost every programming language has a library for you to use regular expressions, and almost every language uses regular expressions the same way. So there's 2 pages. Each page is worth 5 points of extra credit, right? So you just hand it in, and I'll put in 10 points for you if you do all these things. So the only thing it would require if you do it in Java is to learn how to read a file, which is fairly straightforward. But for this section, basically there's a attached word.txt, which is it's a dictionary essentially. It contains all the words that you would basically use in the English language for spell checking, essentially. If you're using a Unix system, if you're using Mac or Linux, and you have a dictionary, that will mean you'll already have a dictionary file somewhere hidden on your computer, and if you want to use that instead, you can use that. I think it's under /user/share/dict. But the point is, I care more about the regex than your answers. So but it's answering questions like this. How many words contain the word cat or dog in them? And you want to write regular expressions that answer these. How many 4-letter words are there? So how do you look for a 4-letter word through this file to identify what a 4-letter word is? Do more words end in ing or ion? How many words contain a Q that aren't followed by a U? Like, for instance, Qatar, the country. That's got a Q, not followed by a U, right? How many words have no vowels? How many words with 2 vowels in a row are there, right? How many words have at least 2 vowels? The vowels don't have to be adjacent, though, this time. How many, so here you're just counting to make sure it's got 2 vowels. But using regular expressions. Now, the big thing to know about regular expressions that I did not mention to the other class is that regular expressions are super powerful, but they're also limited in their power. They have essentially very little memory. For instance, the classical example of where they fail is like parentheses matching. They can't match open and close parentheses and check to make sure so that's where the kind of capability. But it can solve all these problems over here. And I've got a link here. And then they've got more questions over here about these kind of things. Like this one, you just have to look that up. And over here, is another regex problem, and then I have another regex problem over here. So this can be turned in at any point. There's no due date for this one. It can be done in any language, so if you want to take the chance to learn another language, go right ahead. Okay? So that's extra credit. So for this week, on the other hand, for your homework, rather than giving you a programming assignment, because this week's all about big O notation, and yes, I uploaded the videos yesterday afternoon, so of course I have no expectation that you guys watched it all before you came to class. Okay? So hopefully by Wednesday you guys can get the chance to watch that, but you'll need to watch it in order to complete your homework. Right, so let's see if I hold on, if I do environment, and then the lights, if I go to 3, how does that chance? I think that makes things slightly more visible if I do that. Okay. Yeah, if I dim the lights, it makes it slightly more visible here. So here are basically, I put on this front sheet as a reference to you of some rules for computing big O notation. So these first 2 rules I give about only the highest degree mattering and ignoring all factors, they matter for this first page. And then this one matters for the analysis of your algorithms, this 3rd rule. Okay. You can complete these by printing them out and then handing it in, or you can type it up and print it out and hand it in, or you can type it up and then upload it, or you can do it by hand, take pictures of it and upload it. We do not care. Just get the answers to us in some format that we can actually read. Okay? Okay, each of these pages is worth about 20 points, I think? Yeah. So this big thing we should also know is that I fully expect everybody to get an A on this one, because there's nothing stopping you from coming to me or your TA and asking, hey, is this the right answer? And me going, no, that's not the right answer. Do it again, right? So you can check to know. So I am more than happy to check to make sure you're getting an answer, right answer or not. This first page looks like complicated math. I assure you it will be some of the easiest math you have ever had to do in your life, and in your because figuring out the big translating these to big O notation is fairly easy. And I'll get into it, and I'll give a small primer of what that is for those of you who haven't had the chance to watch the video. These will ask you, like, what is the algorithmic efficiency of the array of operating on array lists? How long do these operations take on array lists? And this is all stuff covered in the videos that I've just uploaded. Okay? So I'm not expecting you to know it yet. Analyze this algorithm, analyze that algorithm on this other page. I give you code, I ask you to give me the big O time complexity. And then I ask you, here's a sorting algorithm called BOGO sort. BOGO sort is one of 2 algorithms, BOGO sort and stooge sort, that don't actually exist in the real world. They only exist in algorithms classes or data structures in algorithms class, and they exist for students to analyze. That's because you can immediately tell that BOGO sort is a terrible algorithm. BOGO sort is an algorithm that says, how am I going to sort this list? I am going to shuffle the list randomly, and while it is not sorted, I am going to keep shuffling it until I get a right answer, right? So while it's not sorted, shuffle the list. Okay, that is and once this list is sorted, it stops shuffling it, right? Essentially, this is the equivalent of like throwing a deck of cards into the air, reassembling it, and hoping that the cards are in the right order, right? So it's a terrible algorithm, but I need you to analyze it just so you can understand. And then here is where we get into the other stuff for your I mentioned about your other your assignment on array lists. So 20 points is for each of the methods you wrote in lab 2. So the ones you solved the array list questions. Figure out the time complexity of the method you wrote. Okay. Good news. It's going to be one of 2 options. It's either going to be a linear time algorithm or a quadratic time algorithm. So it's almost guaranteed to be that. But basically analyze the code you wrote for the runtime, which will be great practice for the exam on week 5, because this is I typically ask this. Whenever you write a method in my exam, I typically have a 2-point question after that asking what's the big O of what you just wrote. So good practice for that. All right, so what is big O notation? All right, so I assume you know because you took, right, you took more, you already know how to program some stuff, right?
Growth of a function.
Yeah, growth of a function, right? But you're a graduate student, so you're the only person I would expect to know. I go over. So Big O has these whole formal mathematical terms that you will probably learn. Let me get it actually, so it's actually capturing, me. There's only there's formal mathematical definitions where you learn it in algorithms, but right here what we need is an informal understanding. It's more important that you understand what it feels like than understanding how it actually works. What it is that Big O describes the growth of the algorithm. Okay? So
relatively how many steps is a particular solution going to take to solve a problem. Now I can't just solve this by running it on my computer, because my computer and your computer are very different machines indeed, right? And some computers have different commands built into their processors that might actually be quick. Might be quicker or slower. So that's one difficulty. Another thing is even if I'm just using my computer to time everything, my program, there's a scheduler that schedules what gets, what particular computations get done. And so there will be, millisecond fluctuations or even more in the algorithms I run. So instead what we use is big O notation. And the three we learn in this chapter are O of 1, O of n, and O of n squared. And these describe basically relationships between n, which is the input size, how big the list is, or how big an array is. So n is like the size of the array, or the size of the list. And how long it's going to take, right? N is the size, O of n is kind of the relation, is saying how quickly this is going to grow. Now constant time is possibly the easiest to explain, which is one over here. Although I say this is constant time, we can actually use, as I mentioned, these describe the costs of some resource. Most commonly time, because time is the most valuable resource, since you cannot buy time. There's other resources that computers use, like space or energy, but we can always buy more things. We can always buy more space, we can buy more energy, we can't buy more time, so that's typically the most useful to deal with. Also, people get, they get annoyed when your web page takes more than like 3 seconds to load. So, we feel very differently about time than we do about space. Right? You get more annoyed about how quickly your programs run than how quickly your battery drains. So we typically talk about constant time rather than time. So constant time, what that means is essentially, it doesn't matter how big the input size is, right? It doesn't matter how big the list is, how big the array is, it's going to take the same amount of time to solve this particular problem no matter what. The classic example, at least for me, is the problem, how big is this list? How big is this list? Well, for a list, like the array list, it had a size variable in it, right? A list keeps track of the size variable, and to get it, you just call list.size, which returns a variable. Doesn't matter how big that number is, 100 or 1,000,000. You're just taking one number and moving it somewhere else. It's always a 32-bit number. One 32-bit number is no more complicated to move around than any other 32-bit number, so it takes the same amount of time, no matter whether the size is 100 or 1,000,000. That makes sense to everybody? Getting a variable, doesn't matter how big the variable is, takes the same amount of time. So O of n is a linear relationship. That means that there's it's linear time. Linear relationship between the size of our problem and the amount of time it's going to take, right? Whereas constant time is some straight line over here. Maybe it takes all this time for any input size, or possibly this time. I don't really care what the particular line is. I care about how the line looks, the shape of it. So for a linear relationship, it's going to look something like this, or possibly like this, or possibly like this. But these are all linear. These are all lines that would be described by a linear equation, right? They're all linear relationships. I'll just erase two of them for simplicity's sake, right? The idea here is that adding an additional item adds an additional unit of work, essentially, right? Say I've got 20 students in this class. I think there's more of you, but say I've got 20 students in this class and I've got a grade. And because there's 20 students, come exam time, I've got 20 exams to grade, right? If a 21st student joins the class, I just have one more exam to grade, right? So I go from 20 exams to grade to 21 exams to grade. It's not really it's not a huge increase of work. It's just one more exam, right? If I have twice as many exams, twice as many students, I have twice as many exams to grade come exam time. Make sense, everybody? It doesn't magically blow up. So L of n squared are those that magically blow up. They are the quadratic time equations. And they look like, as you might imagine, a parabola. Okay? That relationship. And again, I don't care like particular if it looks like this, or maybe it's like this, or maybe it's like this, right? I don't care about the particular shape of the parabola. What I care is that the growth resembles a parabola. Make sense? Right? The idea here is that with a quadratic relationship, let's go back to my example of having a bunch of students, right? I have 20, I have, let's say 9 students in my class, and what I'm doing is that as part of what I'm doing, because I'm a paranoid teacher, I'm taking a look at every pair of student, right? Every pair of students, and I'm checking each pair of students to see, hey, are you cheating, right? Did you copy these answers from somebody else, right? Because I'm a paranoid teacher. I don't do that because that takes a lot of time, right? So now, suppose we had 9 students, right? I add a 10th student, okay? That means I have to compare that 10th student exam to 9 other exams, right? Adding one unit of work didn't mean adding one more exam, that means I don't have one more exam to check. That means I have 9 more pairs of exams to check. That makes sense to everybody? And that kind of growth creates a parabola, right? We're essentially adding one more unit of work, adds on basically adding one more item means I have not one more unit of work, but n more units of work to do, essentially. Okay? And that's the kind of growth rate that we get, essentially. Now, you might be asking, okay, that's great, but how can I analyze an algorithm to figure out that kind of stuff? Well, actually, we do that by starting from the back of the rules, the quick sheets the cheat sheets that I have over there. Rule number 3 is the first step, and it will give you actually the stuff in the other step, which is the T of n, which is the number of steps that it will take to acquire. You're like, okay, Professor Rose, looking at like all this code and figuring it out, that seems hard. Surely there's a quick and easy way that's almost surefire to work. And there is. And that's counting the number of nested for loops. Will typically give you the number of, the runtime of a particular algorithm. Okay? Okay? So suppose I have some method over here, right? Here's my method. Right? And I go into way more detail in the slides. Okay? It has no nested for loops. It is so it's almost certainly going to be a constant time algorithm. Suppose it has like 5 steps or 100 steps. That just means it doesn't matter what size, right? Suppose it takes I'll just say it takes in a list L, right? Just to be, right? Doesn't matter what size the list is. If it does the same amount of operations every single time and it doesn't vary based on the size of the list, it's a constant time operation. Suppose then I have a for loop, right? Like for, let's say, each item for each object O in the list. Right? This is an algorithm that works on every object in the list, right? This is a big O of n algorithm, right? Because I have n items, then I'm going to do around n steps of work, right? It could be 3n, it could be 4n, right? There could be 4 statements in here, there could be 2 statements in this block, there could be 100 statements. But it would still be a linear relationship, right? Doesn't matter how many steps, how many things there are in here, it'd still be a linear relationship. We'd be doing the same amount of work for each item, right? Right? Another way to look at me grading the exams, right, is that, like, with the whole grading exam, it was like having one more student means one more exam to grade. I could also look at it as if it's a 20-question test, adding one student means I have 20 questions to grade, right? And adding another student means I have another 20 questions to grade. But it doesn't change the amount of questions I have to grade for any other student, right? Okay, so an O of n squared algorithm looks something like this, a nested for loop. So basically going over, for each object in our list, we go over, so if we have, for each of the n items in the list, I do n operations, right? So this outer loop runs n times. For each time the outer loop runs, this inner loop runs n times. So n times on the outer side, n times, and each of those are n times. So it's n times n, so we get n squared. And it just goes on and so forth, right? Any guesses as to this? Object O, L. the stuff that we're going to see in this chapter, like in the real life examples that we see, they're almost always going to be n squared, right? Or n O of n, or constant time, one of those three. Later on, when we learn about recursion, we'll be introduced to log of n algorithms, which sounds scary, but essentially that means that every step I take reduces the amount of work I have to do by half, which is a pretty good deal. And then we'll learn about log linear time, which is like a divide, where basically we can take a divide and conquer approach. And those basically are, they live in that space between between O of n time and O of n squared. So they grow a bit faster than O of n, but not too much faster. So it's nice, those are really nice algorithms. Now again, I did do a lot of it. I did go over a lot of these in the videos, which you probably haven't had the chance to watch. But so you have access to the videos. You also have access to the slides. Because somebody pointed out last week that they couldn't see the slides, even though I had uploaded them, and so I fixed that. So all the slides for the textbook are now on the Canvas website, so you can download them. They're on the Files tab, and I think slide 67, I believe, is an extremely useful one because it's a table of all of the common runtimes. The last thing I want to go over is that basically these are describing the types of problems we can solve, and kind of they give you an idea of how solvable these problems are. Problems like these, they're where we get something like 2 to the nth power. This doesn't mean it's unsolvable, right? It's going to take a really long time to solve, but that doesn't mean it's unsolvable, right? This means that basically for every additional item I have to do, the amount of work I have to do doubles, right? Because the exponent's over here, right? 2 to the n, right? Add additional item, the amount of work I have to do double. And that's not necessarily a bad thing because a lot of password encryption now, public-private key encryption relies on basically the way you have to brute force crack it is to do prime factorization, which takes 2 to the nth time to do, where n is the number of bits, right? So basically, by using a whole lot of bits, then it's become impossible to crack this algorithm before like the sun burns out, And by then, not only are you, and you've been long gone by then, so that's okay. So the point is that these kind of algorithms, at some point though, these problems can get to the point where they're too difficult to solve for a computer in a reasonable amount of time. Okay, so the algorithms we're dealing with right now, with the exception of bogus sorts, as you'll see, they can be solved in a reasonable amount of time, or they have reasonable runtimes. So you guys can get started. You can show me your work on. So you can also, I'm also open to. So you can ask me questions about this. You can ask me questions about the array list, or demo that, or you could demo the fox and rabbits if you haven't had the chance to demo that yet, assuming you've turned it in. So, I'm just here for whatever.